After the binomial distribution, we will talk about another distribution that is again directly related to the Bernoulli random variable. This is the geometric distribution, and it represents the number of fails in a series of independent Bernoulli P trials observed before the first success. Okay, so here you have a sequence of fails first, and then just one success at the very end. So the sequence is decided for you. Okay, if you change the order, if you move the success to somewhere else, that's a different outcome here. Okay, since we are looking at the number of fails before the very first success, here the order of the sequence matters. Okay, so here we do not have any binomial terms as you observe, and the probability for such a sequence is, since the probability of a fail is 1 minus p, and you have k of them, and at the end you have a success, one success, so the probability is 1 minus p to the power k times p. Okay, and the support here is that means the sample space here is uh, all non-negative integers, natural numbers. Why is that? As long as success is not a certain event, okay, as long as fail has a non-zero probability, the probability that you observe um, a number of fails observed before one success is non-zero for any finite number of fails. Okay, it could be very, very small, but it's not impossible to see 1 million fails and then the first success. Okay, so that is the probability for that is 1 minus p, whatever p is, to the power 1 million times p. Okay, obviously it's a very, very small probability, but it's not zero. Okay, so this random variable is not a finite random variable in the sense that its sample space is a is an infinite set. Okay, it consists of all non-negative integers. Now, at this point, to compute the statistics and observe the properties of the PMF, we have some relations to remember. The first one, um, the sum of the terms a to the power k, where k ranges from 0 up to n, is given by this term. It's not that difficult to prove this. You can use induction or you can use a direct expansion. It's 1 minus a to power n plus 1 divided by 1 minus a. And if you take the limit as n goes to infinity of this, um, provided that the magnitude of a is smaller than 1, strictly smaller, okay, it cannot be equal, this term will go to 0, a to the power n will go to 0, as long as a in magnitude is less than 1. It could be negative, but it should be in magnitude less than 1. And that limit will converge to 1 over 1 minus a. Now, coming back to our PMF, you get 1 minus p to power k times p. If we add all probabilities in this PMF from k equals 0 to infinity, as you see, I'm including all probabilities. As I have stated, this is an infinite set. 1 minus p to power k times p, assuming that p is not exactly equal to 0 and not exactly equal to 1, that makes 1 minus p in magnitude less than 1. So I can apply this result here. Okay, so p here stays constant. It's not, it doesn't depend on k. So I can pull it out of summation. But the summation, this here, will give me 1 over 1 minus p. Sorry, 1 over 1 minus 1 minus p. 1 minus whatever you have here. Okay, so you have this term here, and this p comes to here. You see 1 minus p gives me p. So p divided by p is 1 as expected. So this is the sum of all probabilities in the geometric distribution. So what type of scenarios can we use geometric distribution to model? For instance, the number of coin tosses before first heads or before first tails, doesn't really matter how you define it. So the number of coin tosses before you see heads, or the number of die throws before I get a 6. Okay, here P will be again 1/6. Here, provided it's a fair coin, it's P equals 1/2. Okay, you see the parameter of the geometric distribution is P, the parameter of this Bernoulli trial, underlying Bernoulli trial. Okay, we do not have an n because it can practically go to infinity in the most general case.